now we're going to look at a very specific example, a numerical example, of how to calculate the net electric field at a point in space. So this red dot, this point in space, 0.1 in the x, 0.6 in the y, that is being generated by two point charges. So we have a charge Q1 of negative 1.2 microcoulombs here at the origin, and we have a charge Q2 of negative 0.5 micro. Micro is 10 to the minus 6. We'll have to be using that as well at position 1.1. And what will be the net electric field? Well, electric field is a vector quantity, and as we've done before with all of our vector quantities, we calculate the individual vectors and then do a vector addition to get our answer. Now, we are first going to calculate the full electric field due to each of the point particles individually. So we're going to calculate this E1 over here, we're going to calculate E2 over here, and we're going to get the direction correct into the problem. Now, we know the electric field equation is K Q, source Q. So that's going to be the Q1 at the origin, right? So this Q here is our Q1 at the origin divided by R1 squared. So R1 is the full distance here, full distance here between Q1 and the point in space. Now, there's two ways, as it turns out, to get the direction correct. So we can put it's a negative Q. So right, remember we said you leave the negative in, that means radially inward. So that's why it's going to point radially inward to Q1. We're going to see that there's another convention that we use in physics to determine that direction, and when we draw our own field maps, we're going to get back to using actually this test charge concept that we have over here. So the test charge concept works, so over here. The way the test charge concept works is that by convention, we say that we are going to utilize these test charges that are just theoretical constructs, so that the test charges do not really exist. It is going to be this infinitesimally small positive charge. We don't allow it to have any significant charge, because if it did, it would generate its own electric field and interfere with our answer. So if we put this theoretical test charge at the point in space, well, we know opposites attract, so the force that this negative Q would exert on that positive test charge would be to pull it down right to the negative Q. So we'll get the same answer. At any rate, we do the same thing for Q2 to get the full value of the electric field, the full value of the electric fields for our purple E1 and our green E2, and then we are going to utilize our sines and cosines for the purple E1, right? So the green E2, if I put a positive test charge at that point in space, my negative 0.5 down here will pull it straight down, so it's only in the y direction, so I don't have to worry about that, right? So this is a y direction force only, so that's where this one comes from. My E1 in the x direction is in the negative x direction, so my x direction here is my x direction equation here. It's in the negative direction, and the y direction equation is my y direction component here. And then hopefully this all looks familiar to you at this point. With what we've done in physics, we add and subtract like components to get the net electric field. So, and that's it. We can box that as our answer. That is a complete answer. That's the Cartesian representation of the net electric field at that point in space due to both Q1 and Q2. If we are asked to put it into polar form, and only if we are asked, we would do the Pythagorean theorem. We would do inverse tangent, so I'll leave that to you to confirm, to put it into polar form. And then this last part of this problem has us calculating the force on a particle put at that point in space, and at this was, in this case, they told us it was a proton. So if they told us we were going to put a proton down at the point in space where the electric field is 16,907, F equals QE, the charge on the proton. The electric field is the 16,907, so we get the net force, and of course, it's a line of force, right? The electric field will point in the direction of the force because of our vector equality. And we have our force answer. F equals ma never goes away. So F equals ma does not go away. If we know the mass of the proton, we can calculate the acceleration of the proton once we have our force. So my hope is that with everything we have done in physics to this point, that this looks pretty familiar to us, both in terms of our force calculations, our vector additions, and we will be able to, hopefully after a little bit of practice, problem solve these problems readily.